I would say let's slowly get started. So today we have a lecture by Lorenzo on spectral learning.
Yeah.
And we are curious to see what does.
Yeah. Hi, everybody. Thanks again for the opportunity. I'm Lorenzo Giambagli. I'm a PhD student here in Florence and in Belgium, University of Namur. Here, I'm working with one of the organizers, which is Duccio Fanelli, and his background and also consequently mine, all more related with network dynamics and network analysis. This talk here actually will, I hope that will tell you how some of those concepts might come very handy, very useful in a world of neural network, especially in the world of deep feed-forward, fully connected neural network, which are the main focus of the talk. Actually, you can start thinking about quantities which are mathematically defined, like, for example, eigenvalues and eigenvectors of a network. And those quantities, to me, can be used in this framework as some kind of tracer during the training procedure. So one of the take-home message of this talk, I hope, will be that some of those tools might be useful for pruning. Some of those tools might be useful for training sparse network. But really, the thing is, if you have a huge number of parameters, what you can do is start looking for global quantities and trace them to understand what your network is doing, or even better, to, for example, understand which part of your network are more relevant. So this is the outline of my talk. I will start with a very quick recap on very basic network stuff, because maybe some of you might have never heard about an adjacency matrix. And then I will go to the training of a feed-forward neural network using those concepts. So what I will try to do is rephrase the linear transfer of information inside a network, exploiting those mathematical tools such as eigenvalues and eigenvectors. And I will tell you how you can use them, and consequently how you can compute the gradient with respect to them, which will be, I hope, very, very, very easy when you will see it. Then I will go on with the fact that with those tools you can train a sparse network. And what I would like you to understand is that it's not the fact that I will that those are like state-of-the-art tools, because we have not yet tested them very, very deeply. But I think that the concept is interesting. And then, after all that, I will tell you this might be something that if some of you have been at the conference, might be a little bit have already seen that, but I hope to be still interesting, that you can exploit the same concept even to remove nodes inside your network. So a little bit less conventional pruning, in the sense that usually people are more interested in having sparse network. Here I will tell you that using those concepts, you can also achieve compact. Let's start with the network recap. A network, of course, is something super general and extremely ubiquitous in nature. But one way which you can understand this is by a set of connections. A set of connections which are linear transfer of information, like channels of linear transfer of information from one entity to another one. A very simple network, which is the one here plotted, has 4 neurons. And here, those are the connections. So this is a directed network in the sense that information can flow only from one node to another one, but it's not like, here, what the arrow is telling me is that it cannot flow in the other direction. And you can also have like the so-called self loops, which are connections from one node to itself. Now, this thing here can be schematized in a very clever way using the mathematical tool, which is a matrix, and it's called an adjacency matrix. Now, the adjacency matrix really encodes all the information about the network, in the sense that it really tells you nothing more than which is the strength of the connection from node J to node I. And with J, we'll list the columns, and with I will list the rows. So here, actually, in W23 is in row 2 and line 3, and sorry, in column 2 and row 3. And this will tell you about the strength of the connection from 2 to 3, right? Now, actually, this matrix here, of course, can be I mean, it's not like always true, but in this case here, what you can do is diagonalize this matrix. So you can ask for which is the spectrum of this network, and actually the spectrum of the network will be very useful for us. Now, just to warm up a little bit, let's try what this adjacency matrix can be used for. And what this adjacency matrix can be used for, of course, is to transfer information. Now, I hope that everything that I say sounds very trivial to you. So how do I schematize the action of the matrix to a network? How do I schematize the information flow in my network using this tool? I will have a vector which will encode the activity I want to transfer. For example, let's assume that I have activity localized on node 1 and node 2. This means that I will have a vector with only components, the non-zero components on the first and the second coefficient. Then I will act with the matrix A, which is the one I already showed you, and this will return me a vector which has components on the third and the fourth, which are non-zero components on the third and the fourth coefficient, which really means that I've transferred information right here. Okay, so very easy. Basically, here the matrix is has a structure which is very reminiscent to the feed-forward network, right? So which will be something useful later. Now, if I ask myself which are the eigenvalues and the eigenvectors of the matrix A, this is what I will find. I will find that the matrix has a structure that is like that, and might sound like a little bit, pointless to do this thing here in this context, but really what this matrix here is telling you is that there are fixed channels of information. For example, the first column here is telling you that if you have an activity on the first node, it will rebound no matter what on these two nodes here, so on node 3 and 4. So what really this thing is telling you is that this is one channel of information. So what I can really do, and what will come very, very useful later, is that I can encode the information of the structure inside the eigenvector of my matrix. So if I want some kind of network, it is really possible for me to encode this information there if I know how to do it, and with a little bit of expertise, but it's not very difficult. I can really say that the network is feed-forward, and this will be the core idea of what I will tell you later. Now, let's apply exactly the same concept to a feed-forward layer or fully connected layer. I will have something that is activity on the first component here, so on the first NK neurons, and then I want to transfer to the second NK plus 1, and so I expect that the adjacency matrix of this process will be something like this. And what is really important here is that what really encodes the strength of the connection, so these bundles right here, are inside this block. So this network, which is a non-symmetric matrix, which of course is something I should expect from a directed network, tells me that I have activity on the first NK, and this activity will be rebounded on the last NK plus 1 neurons. Okay, easy. Yeah. Actually, this is like one of the core thing about the process, in the sense that it's a very I mean, it's the right question. Here it doesn't matter at all. It doesn't matter because this transfer of information here. Sorry, can you? I'm not. Maybe is there a microphone? Oh yeah. And one thing in which you can understand this, and it's a very important point for the next part of the talk, is that if you want to describe this activity here, you will have a vector like the one I've shown you, right? So the last component are 0. So for sure, this part here won't count, right, in the transfer, because those columns here will be all multiplied by 0. But here you will have something which is a leftover activity here, but you don't care about this, right? Because you only care about the information that is pushed forward. And so ultimately, what really you will read when the activity will have flown here is the action of the first, is basically exactly the action of this block right there. So really the connection, okay? So in principle, one way which I can, there are several ways always like in which I can express those concepts, but actually what you said is quite important, that here really you can have whatever you like, but if you are concerned with an activity flow, which is the one of a feed-forward neural network, it doesn't matter what you get, what you put here. Yeah, yeah, it would. Exactly. And also, like, if you will want to have a recurrent network, then you will have also other stuff. Exactly. So let's now go into a little bit more difficult regime, which is the deep network. How should I encode these? Now, this can be something very tricky and a little bit strange, but in order to fix ideas, this is the way I will encode everything. I will have an activity on the first N1 component of my vector, which has like a length which is precisely corresponding to the number of neurons inside my network. Then I will act with that. I will act on this vector with an adjacency matrix which has this structure, and this will transfer information here. I can repeat the process, of course, after I have now activity on the last N2 components, on the second N2 components, and so on and so forth until I reach the last layer in the network. Now that I'm at the end, I mean, here I've gained nothing. I've just rephrased the linear transfer of information with this formalism of adjacency matrix. Now, what's about this spectral study? Oh, this is exactly the tricky stuff. I could have done exactly also what you said. Yeah, this is just a matter of, because in order to, I think that going from one layer to multi-layer is better to write it in this way. But from theoretical principle, I could also have done exactly the same. What would have been different is the implementation. So the TensorFlow implementation, which is the one I will be discussing at the end of the whole process, will be a little bit different if I would have chosen one or the other way in which I rephrase everything. But here I'm thinking about the network as a concatenation of 3 different feed-forward networks, like theoretically speaking. But everything could have been the same. Actually, in the paper we thought about is not the whole network. You're right. So we have this matrix here, and the question we ask is that, can we write this somehow using this formalism here? This is something that actually is possible if you think carefully about the way the spectrum of the toy model of feed-forward neural network was. And indeed, actually, you can write down a phi, which has this form here. So a phi k has this structure right here. Then I will have eigenvalues and eigenvectors components. Sorry, I will have eigenvalues like that, and the inverse. So with this structure here, so with this eigenvector structure right here, I can encode the fact that the network is feed-forward. And this might sound a little bit, I mean, the thing is that, of course, like the structure of the connection is encoded in the channel the information flows in, and those are the channels. So if the spectrum is like that, this spectrum here is one of the most general way which you can encode a feed-forward transfer of information, a fully connected feed-forward transfer of information. And this will result in an adjacency matrix that is like that. Now here, for example, the way I'm writing this down is by thinking of the single portion, right? Those ones here are for nothing, which is for everything that is outside the k and k+1 neuron. So basically, it might somehow answer the question you had, like this. For example, here I'm thinking about a single transfer inside a network, but the idea is that the idea is that here with this structure like that, I can obtain something which is a feed-forward network. So the eigenvectors encode the fact that it's feed-forward, and then I introduce eigenvalues, which for the moment are like something that ends up on the diagonal. Those two matrices these are precisely in a very have a very precise correspondence, which can be thought as what they have in this block here. So those two matrices here encodes the same action. I can do this. So this is what I want to do. This is what I wanted to do. I want to describe using the eigenvalue eigenvector formalism, the linear transfer of information of a feed-forward neural network. I started by saying, which is the spectrum of a feed-forward neural network like? And I've understood this, and then I've put this structure inside the eigenvectors of my operator. And what I end up with is a matrix which has precisely the same structure, with the exception that here on the diagonal, now I have the eigenvalues. But I know, this is might be a little bit tricky, but what I know is that those eigenvalues, so what's there inside the diagonal doesn't matter for the transfer of information. What really matters is this part here. But what is not trivial is that actually the way I've written my matrix, so in terms of eigenvectors and eigenvalues, has of course an effect and an impact also on this block here. This will look like something like a magic trick, but yeah. Okay. So now that I have the single adjacency matrix of the transfer of information from one layer to another, and now that I've written it using the formalism of vectors, eigenvectors, and eigenvalues, I simply write down the linear transfer of information using this formalism here. And I also add, of course, the nonlinear functions. But then, in the end, I will compute the gradient, not with respect to the connections, but with respect to the eigenvalues and the off-diagonal eigenvectors component. This is what this is the way I'm rephrasing everything. Someone might say, what have you gained? And I hope to convince you that you've gained several things, which is the one I will tell you in the part of the talk. But in principle, these two things does exactly the same thing. I've just parameterized in a different way my linear transfer of information. The way I've parameterized it is reminiscent of the fact that it's a feed-forward network. Yeah. So, sorry, can you? Yeah, exactly. Now everything is the same. I mean, everything is the same in the sense that I have a feed-forward neural network. I've encoded the linear transfer of information in this fancy way of writing things down, so using eigenvectors and eigenvalues. But now my free parameters are the eigenvectors of diagonal components, so the green block of the eigenvectors matrix, and the lambdas. And there is a correspondence between the lambdas, the phi, and the black block of the matrix of the adjacency matrix. And this correspondence is precisely that. So if you want, after writing this down, you can do exactly this calculation here. So you can ask yourself, which are the weights of the adjacency matrix that I get if I write down this thing here. So here, I know that it might sound a little bit tricky because I'm going back and forth from the direct space to the reciprocal space, but really what you get at the end is nothing but the fact that every single connection depends on the eigenvectors of diagonal components, phi ij. So these phi ij here are the off-diagonal component of the eigenvectors matrix, and the eigenvalues, which I've called lambda start and lambda final. Now, the lambda start are the first nk eigenvalues, and the lambda final are the red, so the last nk plus 1 eigenvalues. In each transfer considered inside my network. Okay. It is a little bit strange to, like, I want to sum up a little the stuff, because it's a little bit involved sometimes, because people ask me about what you've done is like, have you diagonalized the matrix? No, I haven't done something like that. My question was, can I write down using this formalism here a feed-forward fully connected neural network? Or if you want, a single feed-forward fully connected transfer? And the answer is yes. But if I write this down, I find that the way I choose my eigenvectors and the way I choose my eigenvalues rebounds on the links. Okay? The way those two things are connected is this formula here, where phi ij runs on the off-diagonal block of the eigenvectors matrix, and lambda start j runs on the first nk eigenvalues, and the lambda final on the last nk plus 1 eigenvalues. Yeah.
Are thinking something, but you find the basis, and it's like finding a self-list.
Um,
And the five then are linked to the other eigenvectors in the new basis.
yeah, and I'm not quite getting this in the new basis thing. What you can say is that if I started with my network, it's a little bit, I mean, it's a little bit tricky. It sounds very easy, but it's not. It's if you have a single transfer of information, like a single feed-forward layer, like from k to k plus 1, one way in which I could have said everything is that let's add self loops. Okay. These will give me like random self loops. This will give me precisely an adjacency matrix. And this is a diagonalizable matrix. So I can write down this formula here like from the beginning. And the way the eigenvectors and the links, the links in the feed-forward neural net, in the feed-forward layer are related, is this formula here. This is another way in which I could have told everything. If it's better, give me a feedback, because I'm still trying to figure out what the way we have like discovered this is by asking, okay, this network here is not diagonalized. I mean, in principle, when you look at the adjacency matrix, it's something that you cannot write in terms of eigenvalues and eigenvector of a network. But why? Because the network schematization of a feed-forward neural network is really, I mean, it's kind of improper in the sense that you will only care about a linear transformation. So a neural network actually is a way of writing down a linear transformation from a space to another, and then you apply a component-wise nonlinearity. The linear structure does not encode the fact that there are real neurons in the proper graph sense. So the way we've understood that we have rephrased the question is, can we write down an equivalent network and with equivalent means that there are the information flows from the first k neuron and k neurons to the second and k plus 1 neurons. Can we do this? Yes, if we add loops. Okay, and these rebounds on the structure of the links like that, because if you fix the way the phi are, then the multiplication phi lambda phi to the -1 returns you precisely a feed-forward network. Of course, then you can say to me, well, but there are those new loops which were not present in the first place. But what I can prove, I mean, and it was exactly the question which was asked at the beginning, is that those loops doesn't matter when you account for feed-forward transfer of information. I be precise, when you account for feed-forward transfer of information. Okay, yeah. Sorry? Oh yeah, it is. It is. No, W. Oh, so you mean this one here? Sorry, this phi here. Yeah, this actually is a little bit improper. I'd say. Oh, in here, this I should have written AK, and W are the links, or only the off diagonal part. It's yeah, this might be a little bit confusing. Here, the dimensionality of that, it's kind of wrong. Here, the thing is, I'm writing down maybe. Oh yeah, it is. This is AK, which is a square matrix, and this is equal to phi lambda. Here you will have lambdas along the whole diagonal. This is a square matrix. This is square. This is square. This is square. So the dimensionalities are nk plus 1. if you go from nk neurons to nk plus 1 neurons, times nk plus 1. So it's a network, it's a graph with nk plus 1 neurons. So it's adjacency matrix, it's a square matrix with these dimensions here. But I want to extract only the meaningful part of this transfer, which are these links here. And those links here can be computed using this and extracting only this block here. So basically, I will run only on this part here and this part here of the indices. If I do this and I remap a little bit the indices, this will be what the form of the resulting matrix multiplication is. It's a little bit tricky because if I would have written down everything, I should have also remapped the indices, which is a little bit tricky. So if you want to be very precise, maybe we can discuss later, but it's kind of pointless in the sense that here, J runs on the first, runs from 1 to nk, and I runs from 1 to nk plus 1. And so those things there, so phi ij, also runs on the same, how can I say, range, because this is phi ij. So the off diagonal component. The rest is all trivial, so I'm not care. I don't care about this. Yeah.
You're doing a spectral decomposition. Spectral one. Trying to make sure I understand what the linear output decomposition is. There is about writing phi inwards, not translating. And I'm trying to understand why you're being very careful about this. Writing similarity, not like acceptance.
Actually, I would not call this a spectral decomposition. We call this a spectral composition in the sense that I start from a structure of phi lambda and phi and also phi minus 1, which you can prove is exactly 2i minus phi, and then I construct. I show you that this is, if I fix the structure of the resulting matrix, is something I can think of as a feed-forward network with self-loops. This is how the machinery works. It's not that I'm decomposing the network. So it's not that I have a matrix A that is the one of the feed-forward neural network, and I compute the eigenvalues and eigenvector of that. Yeah, this is the single part. Yeah. If you add if you'd have had here random numbers, then yes. It's I don't think that it is an SVD because this is not the transpose of the matrix. No.
It's just using eigenvalues and eigenvectors, trying to make sure that there's a one by one output.
This is I think that it's not an abuse of the terminology, because if I am one thing that is very common in network dynamics is construct a matrix starting from the spectrum, right? Like a graph Laplace, exactly. If I fix the structure of the eigenvectors of the Laplacian, and sorry, can you? Yeah.
And I'm just trying to connect that graph Laplacian spectral one, because the word you can on the spectral one,
Mhm.
the spectral different one.
Mhm.
And say, yeah, this is we're doing kind of like I can eigenvalues and eigenvectors of that system.
I think that like you cannot do it's not precisely the same, because here, if I give you the feed-forward network and I give you only this okay, let me write this down here, this structure right there. Let me do this. Okay. This is something that, I mean, at least as far as we have tried to do this, you cannot write like that. What we have seen is that if you do this, exactly, the diagonal is all zero. Yeah, it's right. It's zero. I mean, you cannot do this. But if you add this, suddenly it becomes possible. But then what you discover is that those stuff here doesn't matter. So we say, okay, we don't care. I have parameters. Yeah. Yeah, those are random, and therefore also those are random somehow. Yeah. Yeah, you can do this. And this is something I still haven't figured out, because if you write down, what I will do later is exploit this correspondence, right, that I'm writing down here, and do the SVD decomposition of that, which will be exactly what you're saying, in the sense that I will do the SVD decomposition of that, but also link this with the fact that I have this loop right there. So another way which maybe this might be clear is that I've found a way to couple links using this formula here. And what I discover is that this is precisely what I would have found if I would have put loops inside my nodes of my graph, of my network, and then I would have done the diagonalization of the whole adjacency matrix. I don't know if this answers your question, but the thing is, SVD and this stuff here results in different outcomes in terms of what you gain. And precisely what I hope I will convince you that way is that if you do the SVD decomposition, you understand in the, of course, like in the starting vector space, which are the most relevant directions that are used, or your linear operator. And then also you do exactly the same thing in the final vector space. So if you remove one component there, you are removing one component in, for example, you are saying that the projection of your input data of your X along this direction in the starting vector space doesn't matter. And also you can do the same thing in this is linked to something in the final vector space. Here, this means that the weight matrices will be different if you remove a singular value of the weights, but it doesn't mean that the network will be smaller. Here, if I find that an eigenvalue, so a component of this transfer of information here is not relevant, I discover that this node is not relevant. And therefore, I can remove a node with this way of thinking stuff right there. So they're not the same. They're not the same. Yeah, in the if in this context here, you're saying. Yeah, yeah. Well, when you say eigenmode, you're about what the composition? Sorry, when you say the eigenmodes. Oh, okay. I see. I see. I see. Mhm. Yeah, but here it's not.
And I wouldn't have needed it in this other picture. So I'm really trying for something subtle and different than graphical processes.
Actually,
Your ability to do something you couldn't do with the other person.
actually, I mean, I have to be sincere. I haven't done this correspondence with the graph Laplacian analysis of that. So there might be some kind of very like immediate thing that you can say, oh wow, yeah, I'm precisely doing the same stuff. I think that they are connected a lot because the way like the graph Laplacian is something you can construct starting from the adjacency matrix. So for sure that there are some connections. But what I think, I mean, I don't know what the graph Laplacian of a network like that would look like, but what I think that what I find here is that using this trick, you can start speaking about an adjacency matrix and you can diagonalize it. Okay, this is one way which I could have said this. Or I could have asked myself, I mean, is there a way in which I can do? You could. Mm-hmm.
But there's other transformations.
No, it's right. It's right. It's right. Here, those are precisely the eigenvalues of this network here, and those are the eigenvector of this network here. For the implementation and for the analysis, what matter is the link between those eigenvalues and eigenvectors with the links. Why? Due to the fact that how the information flows in the network. It starts from there, so no activity on the last, and then it flows. So this is the link, okay? Maybe like in the following slide, everything will be like if I carry out precisely this computation here, what you find is that using like after having done this link between the connections and the off-diagonal components, actually, if you look at it, it's pretty trivial. I mean, let's fix, for example, the starting eigenvalue, the final eigenvalues all to 0, and the starting all to 1. It's telling me that the connection are precisely the links. So it's not like something very, I mean, you're telling me that, okay, precisely the connection are exactly the links, because those are 1, those are zeros. The way those two things communicate is trivial. But if you tune them a little bit, it's less trivial. So they start to an interplay. Why? Because maybe now it's the moment for me to go over, and everything I hope it will be a little bit more clear. So here, with the way you can interpret this is a transfer of information due to the phi, and then an amplification that is done by the lambdas somehow. Okay, and the mix between those two things results in what? In the fact that you are considering two ways in which information flows in your network. One, which is bundles of connection amplified by lambda start here, the second here. And another one, which is bundle of connection amplified from the end here. So if I have a lambda that is 0, it means that I cannot construct, I will not, a lambda final is 0. Let's remove this component here of the transfer, and let's focus only on that. Okay, and this is something which would be very useful when we do node pruning. Okay. Sorry? Oh yeah, for sure. Oh, this 5 to the minus 1, you can. Oh yeah, yeah. If I compute this calculation here, I can extract the weight of the K transfer, and this 5 to the minus 1 is analytic, and it's this. And so I can link the two using this formula here. So I'm using the fact that it's a trivial inverse. Yeah, yeah. Yeah, okay. If like I think that the way that, I mean, I'm still like I've done several stuff, but still like this thing here still a little bit sometimes confuses me. I have to be, and then like it's something that I've done 2 years ago and keep working on that. Still, like it's strange because it really actually, I mean, I think we have time to discuss it. I have not lots of slides. So what really is quite interesting to me is that if you think about networks, like I've always started to say, okay, I mean, networks are something like this topologically defined, right? So there are nodes, and nodes are something where information like lies in, but also there is this correspondence between networks and linear operators. If I have a bipartite network, which is exactly the feed-forward, the transfer of information, this can be made in correspondence with the action of a linear operator. Because if I take the linear operator, which is a rectangular matrix, right? And I interpret the columns as something where the linear operator takes information from, so the first nodes, and the rows are something where the linear operator throws information in, then I can construct a square matrix with the off-diagonal component that are precisely the one fixed by my linear operator, which is exactly the way the IA matrix of the conventional network, so let's ignore all these fancy loops here, is constructed. And so this network is exactly the schematization of my linear operator. But then it looks like in this formalism here, actually the node are not defined as a topological quantity. The information cannot rest in the node. So it's just as a schematization. So what I can do is add loop. And this really somehow links the idea between, so links the mathematics of the problem with the fact that with the topology. And this results in a proper network somehow. So where nodes are something where information can rest in. And what you can, now you have something that you can think about a network, and you can say, oh, can I diagonalize this network, so the adjacency matrix of this network? This is something you can do now that you've added something that somehow looks arbitrary, and you could not do, you could not have done before. And this is something a little bit, I mean, still, I am sincere. I feel that there is something that I'm quite not understanding about this correspondence here. So. Mm-hmm. Sorry. Yes. Oh. Oh, okay, okay. Yeah, exactly. Mm-hmm. Mm-hmm. Yeah. No, sorry, it's something that you can think about, you said?
Well, I'm trying to understand what I said sound like that you're these is how you think about it,
Mhm.
or trying to get some intuition?
No, I think that, yeah, it's like adding a memory in your node. This is true. This is true, but still, you know, like this, yeah. So, please.
Is that at the end rule?
Yeah.
Your reference will, let's say,
I mean, again, this might be something a little bit confusing, but if you fix that the norm of the eigenvectors is 1, then this is, you can diagonalize it with precisely. I mean, it's not that you have redundant parameters. I started like that because in the end, I don't care about all this stuff like here. So the normalization, because in the end, I want to train everything. But if you want to be mathematically precise, then I think that the talks change completely. We should have started very carefully because it's very easy to get lost on those stuff. Like, at least for me, it's very easy. But the thing is, we are not doing SVD decomposition of the links. This is something that we are kind of doing like in slides. But what we are doing is, if you want, adding loops and then construct the spectrum of this matrix and discover that actually with this spectrum, I can precisely do the same feed-forward learning stuff I'm used to. Okay, this is another way in which I can think about this.
It's kind of like the spring. It's a network spring with those things in it, like spectrum. In a really sense, I can't have an actual object in my, I have to have these self-use.
Ah, yeah.
Say, well, if I have a massive spring kind of bizarre.
Yeah. Might be. Yeah. That's nice thing. That's a nice comparison. Yeah. So. Yeah.
So let's make a very simple example. Let's say NK and one is exactly the same number.
Yeah.
Let's say that we implement the factor of convolution. Of course, I understand it doesn't make sense, but satisfying ways to represent.
Yeah.
And all that convolution, I can go into Fourier space.
Yeah.
So the question is, in that simple example, with the numbers, the eigenvalue.
You're very lucky because I precisely like work on this like 2 days ago. I'm very lucky. I should rephrase it in 2 ways. The convolutional neural network is something that you can obtain with this formalism, fixing phi, the off-diagonal components of phi, with the structure of a Toeplitz matrix, so a circulant matrix, and then fixing a certain periodicity in your eigenvalues. And then you will discover that the weights of your filter are the eigenvalues in this context here.
So again, so the I would not expect it to have an equal IKX main.
If you want to work, yeah. If you allow me to work in the complex, yeah. Then yes. Yeah, exactly. The phi would have been that. Let me think of what I've said. The phi would have been exactly, I mean, in the phi's that would have written this periodicity. So the way you pick information would have written some periodicity in the phi. So in the connection space. So yeah, exactly. Somehow, yeah, there will be written in there. So we are working. Okay, yeah, sorry. I'm yeah, with the square thing, yes. Okay. Now, what you can do in order to compare this, let's say, fancy way of writing things down is, first of all, ask yourself, what about the role of those eigenvalues in the training procedure? So basically this amplification, this local amplification inside my nodes, right? And so you can start with this comparison, which is maybe fair, maybe not. Like, I'm here to discuss with you on that, which is picking an exactly the same number of parameters, but in terms of links. So you train a neural network with the same number of free parameters, which are the nodes, but you pick them at random. You train them several times, you do the average, and construct this thing here. What's going on? Okay. So this is what the result if you train a subset of connections in the case of a neural network with one hidden layer. Now, with this formalism here, then I can say, what if I train the exact same number of parameters, but now I train the eigenvalues? This is what you obtain. So in terms of role, those are for fashion amnesty, if I remember correctly, but we have tested also with 10, of course, with not the maximal result because we're not working with convolutions yet, and also with amnest, and the results are basically the same. So here, what you get is quite like the fact that what you can understand is that this global way of writing things down, so those global effect of those eigenvalues, it's better than the local one of the connection. Okay, this is the second message. Yeah. A 3-layer feed-forward fully connected neural network with one hidden layer. So, and this on the X, I'm writing and two, so the sides, I'm changing the side of the hidden layer. They are chosen at random. I fix the number, and then I pick out random few of them. For example, let's fix like the number n2 is equal to 100. So I have 100 eigenvalues. For example, if my network is n1, n2, n3, then in the whole network, I have n1 plus n2 plus n3 eigenvalues somehow, or actually more because I'm considering it as two networks, but let's ignore this. Let's assume you have n1 plus n2 plus n3 eigenvalues. Then I will pick in the whole network, dividing them properly, n1 plus n2 plus n3 connections, and I will train them. I want to understand here if this way of parameterizing links globally is better or not than picking them at random. It's going on autonomously. Well, how is it possible? Okay, I don't know why. The same number of free parameters, so of trainable parameters. So the global one are better. This is what you get with the, yeah? Here in this graph here, I'm training a subset of links which are exactly in the same number as the eigenvalues. Of course, they are a lot less in terms of all the possible ones, but the subset that I choose is randomly chosen, and then I train them. So globally, it's better than locally here, okay? This is the reference for the full neural network, and this is what you get when you train so the phi of diagonal components. So of course, it's basically the same. Okay, now the idea that you have, say, okay, those phi's in the formula here looks like looks like something that encodes the connection. Why not use the SVD decomposition of the connection and mix the two, right? Or maybe another decomposition like the QR decomposition. So we took exactly this and we did the SVD decomposition, and then we did the QR decomposition. So now we have two levels: one, the eigenvalues of the use the pointer, right? One, the eigenvalues of associated with the nodes, and then the one with the links. Using that, in the picture I will show you, I've fixed it at random U and V. You can do something a little bit more clever. We are working on that, but let's skip on this. We train only either S or R. And those are the way that basically we have encoded the idea of, okay, let's find those global parameters and see how they affect the learning process. And what you get is this. So here, I'm plotting the accuracy. Now here is the same network, the same idea. So again, 3-layer, I'm changing the size of the hidden one. And what I'm doing is comparing with the feed-forward fully connected neural network fully trained, so the conventional neural network. And this is what I get, so around 90% of the accuracy, of the maximal accuracy, using only eigenvalues. But what I get training only the eigenvalues and the singular values is that I'm getting a little bit closer. And then if I use the QR decomposition, I also basically reach the limit. So this way of decomposing is getting me more and more accuracy, basically, more and more degrees of freedom, which is something intuitive. But to me, it's also interesting because it's the fact that you can find those global parameters which are less in number than with respect to the number of connections and still basically do the same thing. And as you can see, the way, the cool thing to me is the way the complexity is. Because here, what I find is the ratio between the values, between the number of parameters in the network and the number of parameters that we train. So the full set and this. And the very cool thing is that the eigenvalues part scales linearly with the number of nodes, whereas the connection part is the product. This is something interesting to us, and it's something that we would like to a little bit explore a little bit more, because I mean, there are like two limits in which maybe the net, this is some like more a discussion, but in which the network can work properly. If you enlarge the network, you can have let's say a quadratic scale in the scaling number of parameters in terms of connections, and a linear scale of parameters in terms of eigenvalues or singular values. And those two things somehow converge at a moment. And this is like a very interesting behavior to us. So in the sense that maybe you can do some kind of, bounds for those global stuff, those node-oriented stuff. So the way you can bound the generalization error maybe can be better using this stuff. I mean, those are the idea we had connected to that behavior. Yeah. In this context here, wow. Usually when we carry out this test right here, we employ a validation set, and we use the early stop technique. So that's the way we stop our training. So we want to maximize the validation accuracy. So, but what I'm showing you here, of course, is the test accuracy, not the validation accuracy. If blue is trained for the same number of epochs, I mean, I'm not sure if in this plot here is the case. I'd say yes, but what we have done like later, and the way, I mean, I've always used those stuff here, is using the validation. So in principle, I mean, if you want to be precise about the accuracy, you can also do, like, you should stop when the validation test, when the validation accuracy starts rising. But I think that in this plot here, the epoch is fixed. I can check the paper for you, but I think it's fixed. So if you want to know exactly the number, I would like bet like 50 or 60. I can't remember, but it depends. Like I don't remember, but I can for sure I can give you the exact number. Now, another cool thing about this way of parameterizing stuff, which is something, again, it's not, to me, it doesn't have to be thought about something like, oh my God, I have this fancy. We are really working on like rephrasing everything to be competitive with the state of the art. But this is like an interesting proof of concept I thought you might like, which is the fact that using those global parameters, local constraints are less important. So you can achieve this fact that the gradient flows along the eigenvalues, which are something that has a diffuse effect on the network, and you can exploit this in order to avoid local constraint. So to train sparse network. So usually the way we have phrased the problem is that, for example, that let's assume you have a connection in your network, let's call it Wij. I will pass this connection to a filter. And this filter is like that. So it has some kind of bounds, and then it's the identity. So if the connection falls here, the gradient is 0. Okay. So it means that with conventional training strategies, there are, of course, fancier way of training and of like remembering the gradient, but let's ignore them for now. This connection cannot be updated. So you fix the sparsity using this formalism here, no way that this connection can be updated. If you think about the spectral decomposition way of writing down the linear transfer of information, either with SVD or with or also like with the eigenvalues, or also with SVD or QR, the behavior is different. Because of course, here no way that the only way in which you can train the W connection is by if it is length there. So otherwise it cannot be updated. But if you use the lambda and phi with formalism, actually the gradient of the lambdas, so of the eigenvalues that has an effect on that connection, can be different from 0. So during the training, you don't know from the beginning which will be the topology. Because it might be that connections can vary due to the local effect of an eigenvalue. Okay? Training. So there are two, in a single transfer, there are 2 eigenvalues. And so let me show you which are those non-local effects. The start ones, remember, are those bundles of connection here. And the final ones are those bundles of connection right here. So basically, if I change this eigenvalue here, so the red one, can have no 0 gradient due to all those connections here. Not only that, so that's why it cannot be, it can be updated. So let's try this way of writing things down. So how can I train a sparse network? The way we rephrase this is fix a percentage of sparsity. And then during every train step, we compute the distribution of the W's, and we find the percentile so that the percentile of sparsity is fixed. So now someone might say, here, like there are some ways which can now become trainable due to the fact that the distribution is changed. This is true. So here we are doing a little bit a step further. It's not necessarily true that the topology will be exactly the same. So we are like, of course, to compare, we release a little bit this constraint. So we will have, like, during every train step, this bound which can shift a little. They depend on the value of the connection. Remember, on the value of the connection. So those are the results, and the results are pretty interesting to me, because with this way of parameterizing things locally, actually what you can get is that if you train in the direct space, so using exactly the gradient of the connection, there is a strong drop in accuracy when the sparsity is very high. Whereas in the other settings, the sparsity, like the accuracy is very, very much more stable. And I mean, these can be a little bit tricky, but for now, these first 2 minutes, let's focus on the first 2 data sets. Here we have a feed-forward neural network. And if I remember correctly, again, here we are in the 3 layers regime. But what is fascinating is that really and the important thing here, like this red curve is employing either the eigenvalues and the composition, the SVD decomposition there. Okay, so here we are exploiting the full global parameters, basically, the more global parameter we could have. Now, with the CIFAR10, again, of course, the same strategy. The maximal accuracy, of course, is absolutely far from the state of the art because we're not employing a convolutional neural network. So it's just a concept. But the thing is that the way it scales, it's basically the same. So those local constraints are very much less important during the you will look for eigenvalues. And this is something we believe could be relevant for, and we will be working on that like soon to develop some kind of sparse training algorithms, which is something like I find pretty cool. Now, let's finally arrive to the idea of removing nodes, now that I've introduced you everything. So the thing is that now there are some kind of assumption that I will make. And the first assumption is that let me start by training only the eigenvalues. So those local amplification parameters here, those local in my connections. And let's work with the simplified case where every lambda start is 0. So in each transfer, every start eigenvalue is 0. So what I can really account for are amplification of single bundles of connection starting from the arriving neurons. So all the red bundles that I've shown you on the length triangles. So my guess is that if I do this, in the first part of the training, the optimizer will exploit the random direction, so the random phis, which are the random bundles of connections that are useful. and the other one will not be exploited. So this is my guess. So I assume that there is a proxy for the relevance of these bundles, which ultimately is a proxy of the relevance of the node, which is the magnitude of the eigenvalue. So the bigger the magnitude of the eigenvalue is, the more the bundle of connection is relevant, is important, okay? The speculation that I ask you to like at this level believe, to you say to let me do, is that this is something that also is true when I train fives, which is not obvious at all. What happens then is that if I want to have a smaller network, my algorithm is that you tell me which percentage of nodes you want to remove. I will compute the distribution of all the eigenvalues, and then I will find the percentile of this distribution P. And so I will remove every node that has, of course, the magnitude smaller than this percentile. So this will remove the last, for example, the less relevant 30% of neurons. Now, of course, there are two ways in which I can do that, as I told you. The first one is that I train the lambdas, I compute the distribution, I evaluate the magnitude, and then I remove the nodes. And now that I have a smaller network, I train everything. Oh, yeah, please. Sorry, can you repeat them? You have the notion. There's a in each transfer. Yeah. Here I'm fixing the first one always to 0. Always to 0. So now I have a one-by-one correspondence. What with, then I'll tell you what happens if you put them together. Or another thing that I can do is, I remove the eigenvalues, which means that I remove nodes. And this is really, it's quite obvious, right? If I have an eigenvalue that is 0, it means that all the connections then are multiplied by 0. So all this information passing here, it's not relevant, right? So I can really remove this node. And this is something also I can do when I train both. So if I train eigenvalues and eigenvector, I still have this strategy. I evaluate lambdas, and then I remove using the magnitude of the eigenvalue. With the direct space, we wanted a comparison, and the comparison we choose, it's something that it's not the state of the art. Now here I had two problems. The first problem that I had was the fact that node pruning is not very, as far as I've seen, is not very common, in the sense that I couldn't find like state-of-the-art algorithm, and I found one or two, but like we had, there was no code available. So this is an idea we abandoned actually at the very beginning. But the way we rephrase the problem is we want to have something deeply connected to the network, so a network-oriented observable, which is the absolute we've picked to be the absolute incoming connectivity. So our idea is, okay, the same idea when you train connections could be if the absolute value of the sum of all the links of the incoming links is very small, it means that it's not relevant. This is a guess again. So this is the comparison in the direct space. Might be fair, might be not. This is something, of course, that we can discuss on, but this is the comparison. And so again, I train everything. I compute these for every node, so the absolute incoming connectivity. And then if this is smaller than a fixed percentage, I prune the node, so I remove the node. And those are the results we get. And these results are actually very general as far as we have explored. And so let me comment on this. So what do we have here? Here we have, again, a setting of a feed-forward neural network with 3 layers, but we have tested also with different configuration. And also in this case here, we have also tested with different topologies, in the sense also with convolutional neural networks. But let's put them aside for a while. So here, let's fix on the fact that we have a 3-layer feed-forward neural network, and let's focus on this data set here. Here we choose ELU as activation function, but everything is the same for the ReLU function and the hyperbolic tangent for the sigmoid one. I believe that actually the way this thing works simply needs increasing activation function. But this is a speculation, but I mean, if you want, you can discuss on that. I think that this is the point of everything. So I'm expecting that with something that is like a Gaussian activation, this method won't work. But anyway, what we find is that basically, if you used as a proxy the absolute incoming connectivity, this is a terrible proxy, and this is particularly true now. Actually, I speak, I think that this is actually deeper than 3 layers. I think this is 5. Is particularly true for deep networks. So for deep networks, the absolute incoming connectivity is a terrible proxy. But what is remarkable is that this eigenvalue stuff is quite a good proxy. So really, let's focus first on the blue curve, where you train eigenvalues and eigenvectors. It really seems that you can do much better. So you can move like the half percentile of the nodes, half percentage, like 50% of the nodes, and the accuracy is exactly the same. And then you start with this drop here. But now there is the green curve. Now with the green curve, I had it's a terrible plot to me. And why? Because it's a little bit unfair. It's a little bit unfair because, and this is like a discussion we have with the engineers, but I think that the way we will release those results will fix these. So please be kind with me on that. But the thing is that here, what we are doing is comparing 2 curves, which are the result of a single training, with one which is the result of 2 training procedure. One which is training only the eigenvalues, and then training the leftover eigenvectors, so the leftover components of the phi matrix after the pruning. And this is the green curve. So this is something not very, how can I say, it's a little bit unfair. But what I think is the cool part is that the number of parameters that we train is super small. Especially, so let's for example fix the 60%. So here we are removing more than the half of the neurons. What happens here is that I start with the eigenvalues, I train only them, I compute the distribution, I remove the nodes which to me are not important, and then I will train only the leftover network. So I have now, I start with, I don't know, 100 nodes, I remove 60 of them, and then in this procedure here is something that has cost me like nothing in terms of parameters, because it cost me like 100 parameters, because this scales with the number of eigenvalues. Then I use the full power, this was the idea, I use the full power of the training procedure with the leftover network. So in terms of number of parameters, actually, at the end of the training, this curve here uses much less than these 2. So this is why it's a little bit tricky. Like for example, here, let's assume I've removed like 80%. What does it mean? That then I have, for example, 20 neurons, and then I have n1 times 20 parameters. Because the phi's, so the eigenvectors component scales like the connections. Here, I start and I train n1 times 100, and then I remove, but I've trained n1 times 100. Okay, so the number of parameters. If everything has been implemented in TensorFlow, you can find these. Oh yeah. Yeah. The starting, yeah. Mm-hmm. Yeah, actually, I mean, yeah, this is a good question. This is a good question. What we have found is that no, I mean, it's not very important to train to have both. It's important is to have this node to eigenvalue correspondence. So if I train everything, so if every layer, so for every layer, for every set of neurons, I can make a correspondence with the arriving, so with the first transfer of information, and so with the final eigenvalues of the first transfer of information, or with the starting eigenvalues of the second transfer of information. Like I have this ambiguity here. That's why we fixed 1 to 0, so that in every layer, in the fully connected fit-for fashion, there is a one-to-one correspondence between nodes and eigenvalues. If we implement the two, actually, the strategy we've come up with is doing the end of the condition. So both have to be below the threshold. And this works, I mean, basically the same. So, but I'm not like still very preliminary results on that. But the thing is that we care a lot about like in doing these tests here. We are very much concerned with this one-to-one correspondence. That's why we avoided the first part of that. So to conclude, we made everything in TensorFlow. You can easily install this to test this, and you find the function are implemented. I mean, as far as I've tested, they work with every functional model. So also with the sequential model, but if you use the functional API, they still works. So you can do like branches or whatever you like, and they will return you the pruned network, so the smaller network at the end of the pruning strategy. And then the layer is very easily implemented, because in terms of implementation, actually, we only implemented the closed formula, so the one that links the connection with the eigenvalues and eigenvectors. And this is like very easily implemented. It's just a row column multiplication with a vector. So in computational, in terms of computational speed, it's basically the same as the conventional dense one. Actually, we found that there is a guy who is doing this with PyTorch, not with TensorFlow. With PyTorch, it looks like if you train all the eigenvalues, it's faster than with the conventional dense layer, which is something in theory I would have expected also for the TensorFlow case, but I'm still don't figured out why the fast is basically the same for TensorFlow, whereas you train both eigenvalues and eigenvector or all the eigenvalues. But in terms of speed, is basically the same. Yeah.
Let me ask you why. I don't understand why this is as fast as the normal direct space approach. So you don't need to diagonalize and re-diagonalize, or what's the trick?
Because we are not diagonalizing everything and nothing, right? As soon as we have the correspondence between links and phi, our values, like we forget about the links, and the transfer information is written only in terms of phi and lambda. So there is this concern of like being faster is just a concern actually that I have inherited from engineers, which told me, is it faster, is it slower, why should I implement this? And no, because this is analytical, and actually this is exactly the thing we have exploited to write down that this Wij equal lambda start minus lambda final phi ij. This is what you get when you do this computation, and you extract only the meaningful coefficients of the resulting matrix, which are the one that encodes the connection strength. So do you remember on this? So if you open the layer, you will find that it's basically a dense layer, but we have, instead of having these as TensorFlow viable, so the kernel part of the TensorFlow layer is replaced by a new, let's say, kernel, which is the product of this matrix here. So I have J of this matrix here with these two vectors, column-wise and row-wise.
Any constraints on phi ij?
At all, no.
So in other words, if you think about spectral and someone just tells me what there's a little hack, you could write the Wij in this form.
Yeah.
That would be enough. Right?
Exactly. Indeed, I could have another, like one thing which maybe I would have speak much less, of course, but maybe another way which I would have I could have said everything is that, trust me, there is this fancy way of writing down the connection. It's this one with those new parameters. It's a little bit redundant, but it lets you do this very cool stuff, because there is this correspondence between this with a single node and this with another node, and everything works amazing. And this is what you get. Everything would have been the same. to me, it has been very interesting, the flow we had from network, what does it mean in terms of parameters, why somehow like a matrix that it's not diagonalizable becomes diagonalizable. So I think that this worth the experience, let's say. But but anyhow, this is another way of saying, parameterize them in this way so that you get. And indeed, actually, I think that this is another important message. Like maybe one way in which we can analyze the behavior of the neural networks is simply adding parameters which have a meaning that somehow is, okay, let's multiply this by a constant. And then the gradient will exploit that. So if I find a change in something, it means that somehow this thing that I've introduced, which to me has a meaning, can be interpreted. And this is the way why at the very first I said that maybe you can exploit those stuff here, those eigenvalues as a kind of tracer inside the procedure. Because I think that this can be also something more general. You have some, a node or an operation, let's multiply it by a factor. If this factor is very big, it means, it might be, that this part is relevant. So you can really start putting, I mean, to me, it might be useful to start understanding which are the properties of the network in terms of like which are the part that do something, which are the part that doesn't do something. You introducing like multiplier, introducing a tracer, which are nothing but multipliers along the way. This is another way in which I could have rephrased everything, of course. So everything is implemented, very cool. Blah. Then you can find it on a GitHub repo. I hope that sooner we will release a series, like sooner or later, I mean, in 1 month, hopefully, a series of tests with the state-of-the-art pruning strategies, because we found actually that employing, for example, a regularization on the eigenvalues with this technique really lets you prune a lot. So we believe that we might be also competitive with state-of-the-art techniques, so that we will for sure release them on the GitHub repo, so you can follow this. And now the future outcome are for sure extended to the convolutional neural network, and this is something we have basically done. And indeed, there is this fancy connection we have discussed before. So convolutional neural network can be thought basically as a fixing the spectrum and then having a local multiplier, which you can interpret as the eigenvalues of the corresponding feed-forward neural network. This would be a very would be very fun for me to to explain the convolutional spectral layer. I think lots of tricks, but maybe it's easier, we would say. But anyway, then we would like to test it also embedding this in a more advanced structure instead of the good old like feed-forward 3 or 4 or 5 layers. I mean, we wanted to test it with transformers or with fancier networks, and hopefully add a multi-support implementation, because there is a guy who has written this in PyTorch, and there is also a Julia enthusiast who has written it in Julia, but still he hasn't released it yet. So I mean, maybe I hope that in the future there will be lots of different packages, and also the idea that I told you that maybe parameters can be useful to bound somehow the generalization error. I don't know. This is something also that maybe will make the calculation, the analytical calculation, easier. Maybe. So this is another thing. And this is like those are my collaborators. Those are from like, those are also here. So Lorenzo will give a talk actually on another implementation of that on the recurrent neural network the next Monday. And this is one of the organizer. And this is Lorenzo Buffoni, who is also here. I think not today, but it will be sometimes he's around. He's from he's doing his postdoc in Lisbon. And this is my advisor in Belgium. He's like super into all these graph mathematics and so on. So of course, we work as a team, and this is like also their achievement. So thank you very much, and thank you again for the question, for the interesting discussion, and yeah.
Well, thank you very much. There was a very lively discussion, but if there's any further questions, we can take them now.
More like a curiosity about the convolution, when it's going to be ready.
Yeah, actually, I mean, again, this bifurcation here, which is the one I think you have grasped, is the fact that with convolutional neural network, you can You can do, again, two things. You can start saying, is it possible for me to write them down and doing this correspondence with these local parameters? And what you discover is that if you fix the structure of phi and you implement some kind of constraint on the eigenvalues, and this constraint is that basically they have some kind of repetition, so they are the same, then you have exactly the same. I mean, I can prove you in 2 minutes, I think, that you have exactly the same thing. So convolutional neural networks, somehow written in this way, are pretty. I mean, in the end, they are just a fancy way of choosing your phi. So basically, it's something that, I mean, to read like, if I say this in this way, it looks like, wow, we are super general, but it's not like that we are super general. It's not that if you think about a network and I mean, the way in which you can describe a network in terms of spectrum, of course, right, really encodes the way the network will behave. So if you want something that is that has some kind of periodicity, you can impose it either in the adjacency matrix or in the spectrum. So it's quite easy. And in this framework there, it's fascinating that everything that I've told you about, like this pruning stuff, which here is something connected with nodes, here is something connected with filters, so with links, let's say. So somehow this is telling you that the convolutional neural network are already written in the reciprocal space somehow. So the eigenvalues are exactly what you train when you train the filters, which is something that can be intuitive maybe for someone. Or what you can say, this is another way in which you can think about them, is saying, okay, I mean, so the way you have suggested, let's think about the phi as the connections. Those phi will be the convolutional part. So phi ij will be the convolutional. So I will transfer the degrees of freedom to the phi, to the connection. So I will have connection with the same periodicity, so with the same structure. And then I will add on top of that some kind of loops, which are the eigenvalues. And maybe this will make you do something a little bit fancier, because you can remove connection but also portion of images, because then the eigenvalues will be in correspondence with portions of the results of your convolution. So we have those two ways we are working on that. Mathematically, we have phrased them, so in the sense that we've done this correspondence between weights, links, topology, and so on and so forth. And the implementation to me won't be that bad, because we will exploit the convolution layer. So I think the theoretical paper will be out pretty early.
Okay, more questions?
Thanks. Yeah, so this is, I guess, more testing my understanding. If I were to do great violence to your understanding, you just try to like reduce this down to a recipe, would you agree with the following description of what you end up doing, which is, let's say I just initialize a random network, just everywhere where I act with a weight matrix, just multiply that by some diagonal matrix, tune the diagonal values there, throw out all of the nodes where those fall below some threshold, and then retune the weights.
I say that I agree, but this is a little bit tricky in the sense that, yeah, I mean, if you fix this, look at this formula here, or even better, it's bigger. This formula here. This is not the Einstein summation convention, right? So this is a one-to-one. So if you fix to 0 the final, then you are multiplying each weight. So each input, I mean, okay, maybe it's better here. So you have final set to 0. What this is telling you is that, okay, you have a diagonal matrix, lambda, that acts on X, and then you have the conventional weight. Okay, or set to 0 the other, then you have a diagonal matrix that acts on the action of the weights. So you can either take the conventional dense layer, add before it a diagonal, or after it a diagonal. And those two are a one-to-one map between what I'm doing here, fixing the one eigenvalue to 0, and what you do, right? Both together, a little bit trickier. Both together, a little bit trickier, because you have to sum those two or subtract those two actions.
So I would suggest you just doing one of those diagonal.
Ah, okay.
Which does sound like what you do.
Yeah, yeah. If you fix 1 to 0, precisely, it's like multiplying with a diagonal matrix that, and then if this is more than a threshold, remove it. You are perfectly right. Yeah.
Thank you. Any other questions? That doesn't seem to be the case, so let's thank Lorenzo.
Thank you. Thank you.